Welcome to The Explainer. Today, we're building your ultimate study guide for mastering measures of central tendency using real-world data. We're going to strip away all that math anxiety and build a structured cheat sheet that you can rely on, whether you're tackling geography, economics, or honestly just trying to make sense of the statistics we get bombarded with every single day.
Here's the quick game plan for today's guide. We'll start with making sense of data, then calculate the mean, tackle the mean for grouped data, and wrap it all up by finding the median. Let's get right into it.
Part 1. Making sense of data. You see, our very first step is understanding the core problem here. What do we actually do when faced with massive amounts of varying data? Think about measurable stuff in the real world for a second. Rainfall, elevation, population density, or even levels of educational attainment. These things just vary wildly, right? When you're staring at thousands of different measurements, your brain is literally begging for a way to comprehend the big picture. I mean, you obviously can't just memorize every single data point. We absolutely need a reliable way to summarize them effectively. To analyze all this wild data, statisticians usually rely on three main techniques. You've got measures of dispersion, which look at the internal variations, kind of like the spread. Then there's measures of relationship, which show us the association between two phenomena, like how fertilizer consumption affects crop yields. But for this explainer, we are locking our focus entirely on that first, absolutely foundational technique, measures of central tendency.
So what exactly is it? The crucial takeaway here is that this single representative figure acts as an anchor. It's the exact point where all your data items actually have a tendency to cluster. Instead of getting distracted by extreme outliers on either end of a spectrum, this technique just hunts for the center. It basically gives us one single, magical number that we can point to and say, hey, this right here represents the whole shebang.
Now, these measures of central tendency are also known as statistical averages, and you basically have three main tools for finding that center. The mode is the easiest. It simply looks for the maximum occurrence or frequency at a particular point, basically the most common value. But to really conquer your data analysis, we're going to roll up our sleeves today and master the underlying math behind the other two, the mean and the median.
Moving on to Part 2, calculating the mean. Let's see how we build this first major concept, specifically for ungrouped, raw data.
The mean is, well, it's your standard, everyday arithmetic average. The formula here is super straightforward. X, which represents the mean, equals the sum of all your raw scores, that's the sigma x, divided by n, the total number of observations. It's an incredibly powerful little formula, and we can actually calculate it using either a direct or an indirect method.
Notice how the indirect method offers us a genuinely brilliant shortcut here. The direct method is exactly what you learned back in grade school. Just add everything up and divide. Boom. But what if you have a massive number of observations with huge values? The math gets clunky real fast. That's where the indirect method comes in. It uses a clever technique called coding to shrink those large, unwieldy numbers down to size by just subtracting an assumed mean constant from them.
Let's look at a real-world example to see this in action. Take the normal rainfall across 7 districts in the Malwa Plateau. The raw data values are all hovering somewhere between 800 and 1100 millimeters. If we use the direct method, we've got to add all those large numbers to get 6,484. But check out that third column. If we just select 800 as our assumed mean, we simply subtract 800 from each district's rainfall. Suddenly, indoors at 979, it's just 179. THAR is just 33. We're now working with much smaller, wave-friendlier deviations.
By following these three simple steps, our calculation becomes so much faster. First, we picked an assumed mean of 800. Second, we added up those small coded deviations, which gives us a much more manageable sum of 884. And finally, step 3, we just plug it into the formula. Our assumed mean of 800 plus 884 divided by our 7 districts.
And you know what? The absolute magic of math here is that whether you add the raw rainfall data directly and divide by 7, or you use our indirect coding shortcut, the mean rainfall for the Malwa Plateau comes out exactly the same, 926.29 millimeters. Seriously, this indirect trick is an absolute lifesaver on exams when you don't have a calculator handy.
All right, Part 3, mean for grouped data. But wait, what happens when our data isn't just a neat little list of individual districts?
What if our data is already pre-packaged into ranges, completely hiding the individual values? Well, this right here is the secret key to solving grouped data. When you're looking at a frequency distribution, you literally don't know the exact value of every single observation. They've lost their individual identity inside their group. So to do our math, we have to find the precise midpoint of each range to step up and represent that entire group. For instance, let's look at the wage rates of these 99 factory workers. We don't know exactly how many rupees each specific worker makes. We just know, say, 10 workers make between 50 and 70 rupees a day. So what do? We find the midpoint of that class, which is 60. Then we multiply that midpoint by the number of workers in that frequency. This gives us our FX value. For that first row, 60 times 10 gives us an FX of 600. We just repeat this simple process for every single wage bracket.
Using this structured 4-step procedure ensures you absolutely never get lost when navigating these frequency tables. We found our midpoints, we multiplied them by the frequencies. Next, we sum all those FX values up, which gives us 10,160. And finally, we divide that massive sum by our total number of observations, which, remember, is our 99 total workers.
So dividing 10,160 by 99 gives us a very straightforward average wage rate of 102.6 rupees per day. It's actually amazing when you think about it. By using the midpoints as representatives for the grouped classes, we were able to calculate an incredibly accurate arithmetic mean without knowing even a single worker's exact daily wage.
Okay, moving on to our final segment, Part 4, Finding the Median. We're shifting gears now from arithmetic averages to positional averages. You'll want to lock this definition into your memory right now. The median does not care about the actual mathematical value of extreme outliers at all. The median is all about locating the literal physical middle of your dataset. It simply takes your arranged series and slices it perfectly into 2 equal halves. Because it's a positional average, the methods for finding it actually differ drastically from the mean. Now, grouped median formulas can get a little complex, requiring you to calculate lower limits and track cumulative frequencies. So for today's guide, we're going to keep it simple and focus strictly on mastering the foundational ungrouped method. Let's picture this. Imagine you're handed these 7 completely jumbled elevations of mountain peaks in the Himalayas. You've got values bouncing all around, from the 7,000s up to the high 8,000s. Your mission is to find the median height. If you were trying to calculate the mean, you just add them all up. But for the median, we've got to do something entirely different.
Step 1 is absolutely critical here. You must, and I mean must, arrange the data in either ascending or descending order first. In this case, we've lined the peaks up from the shortest, it's 7,817 meters, all the way to the tallest at 8,848 meters. Once they're neatly arranged, you apply our simple positional formula, the value of the n plus 1 divided by 2 item. We have 7 peaks. 7 plus 1 is 8, divided by 2 is 4. So the formula points us directly to the 4th item in our newly organized list. Counting to that 4th position in our ordered list gives us our median height, 8,172 meters. Just look at how this number stands perfectly in the middle, completely unbothered by the extreme values on either end. It has exactly 3 peaks shorter than it and exactly 3 peaks taller than it. Oh, and a quick side note. If we had an even number of mountains, say 8 peaks instead of 7, we would simply take the arithmetic average of the 2 middle-ranking values. Super simple.
So what does this all mean for you? Well, statistical averages aren't just arbitrary formulas you memorize to pass a test. They are the exact tools you need to make sense of the wildly chaotic data in our world. Whether you're tracking rainfall across a massive plateau, analyzing hundreds of factory wages, or measuring the gigantic heights of the Himalayas, choosing the right measure of central tendency literally unlocks the story hidden within the numbers. So, the next time you're faced with an absolute wall of data, which tool will you choose to find its true center?